me, accidentally stopped sharing my screen and I didn't mean to. What I'm going to talk about is these three capabilities here: cooperation, coordination, and negotiation. So these are three fundamental capabilities which we would like to be able to give to software agents. And my question is, how do we give those capabilities? What are the algorithms, the data structures, and so on that might be required in order to build agents that are capable of cooperation, coordination, and negotiation? Okay, so firstly, let's have a look at a particular scenario. This is a realistic scenario. There's a great deal of ongoing research around this scenario. It's called disaster robotics. So the idea is, if you think about a scenario like the Kobe earthquake in the mid-90s in Japan, or the tsunami in Japan in 2011, and the Fukushima nuclear reactor disasters, or the explosion in Beirut this month, you've got a disaster scenario where a building is perhaps partially collapsed. You've got people that are trapped in the building. You've got fires breaking out. You've got a building whose layout has been fundamentally altered by the disaster, and so on. So in such a scenario, it's very dangerous to put human rescue teams, human search and rescue teams, into such a building. It's very dangerous. And so ideally, what we would like to be able to do is to build robots that can do that for us. And so that's the dream of disaster robotics. So the dream is, in this scenario here, where you've got people trapped over here, you've got people trapped over here, you've got people trapped over here, you've got multiple fires in this building. The idea is that the robots would go into this building and they would explore. And they would find the survivors, maybe talk to human rescue teams who, once survivors had been located, could make plans to come and rescue them, or perhaps they could provide treatments for those human teams directly. So that's the dream of disaster robotics. And it's very natural to think about these teams of robots being able to cooperate in exactly the same way that human teams, human rescue teams would cooperate. So human rescue teams going into this environment would very naturally share information with one another. So a robot exploring over here would share the fact that it had found a survivor with other robot rescuers. A robot finding these two over here might inform that it had found some trapped survivors, and so on. So how do they organize themselves as a team in the same way that a human team would organize themselves? So that's the question of cooperation. And two fundamental capabilities are required. The capability to share information and share knowledge. And how do you do that? How do you do that without just sharing everything? Because you don't want to just share everything. You want to share knowledge that you've acquired, the knowledge that a particular survivor is over here. And how do you share tasks? So as you find a particular stairwell over here, which perhaps is blocked, how do you share tasks such as sharing, as clearing this stairwell, so that other robots can come and help you clear this particular stairwell? So that's the issue of cooperation, and two fundamental requirements: sharing information and sharing tasks. And if you think about it, those are things that a human team, a human rescue team, would very naturally do. The problem of coordination is a fundamentally different one. So here we've got a very simple scenario, and this is a warehouse which has two robots in it. And these two robots are owned by different companies. So these two robots are servicing this warehouse. They're keeping the shelves stocked within this warehouse, but they are doing that using with different preferences, with different goals, with different priorities. The company owns this robot here does not care about the company that owns this robot here. Okay, so the task of this robot in the top left is to service this entire space, to simply traverse this entire space infinitely often, and it has to return back to its starting location to restock periodically. So it wants to traverse this space, in particular to go over to this space here. So think about this robot as just simply wanting to go to this space over here and then back into this space over here and back. Conversely, this robot over here needs to be able to do the opposite. It wants to go up to this space here and then back to this space and then back to this space, and it wants to do that infinitely often. So how should your robots think about being able to operate in that environment? Well, the first thing to say is that the standard way that people think about this is, can this robot over here find a plan, find some way of being able to guarantee to achieve its goal, to go over to this space and then back again infinitely often, so that it can guarantee to get its goal achieved? The problem is, in this environment, it's not very hard to see that you can't do that. That doesn't work. There's no plan that this robot has which is going to guarantee to be able to achieve its plan, because it depends on what this robot does. If this robot just stops here, then this robot is never going to be able to succeed with its goal. And conversely, this agent can't guarantee to get its goal achieved either, right? So the standard way of thinking about that problem is not going to allow those two robots to be able to achieve their goals. So these two robots need to be able to think about what the other robot is doing. They need to be able to predict, to model, and to understand each other's actions. Okay, this robot needs to understand and take into account the goal that this robot has over here. It needs to be able to take into account the goal that this robot has over here. And when they do that, when they take into account these others' goals, they can find a way to achieve both of their goals successfully. So it's not hard to see how they might do that. For example, this robot comes over here and waits. This robot goes over here. Then this robot goes over here. And then they do the opposite. This robot goes over here and waits. This robot comes back down. Then this robot goes out, and so on. And they just repeat that infinitely often. But they can only do that if they take each other into account, if they predict, model, and understand each other's actions. And being able to do that is what's called coordination. Coordination requires being able to think about how the actions of one robot will interact with another robot. And these interactions can either be positive or they can be negative. So, for example, the actions of one robot can enable the actions of another robot. So by this robot getting out of the way, he enables the goal of this other robot, right? It wouldn't be possible if he didn't get out of the way. So that's an enabling relationship. But there are other types of positive relationship as well. So another type of positive relationship might just be a promotion relationship. So one robot might do something which helps another agent to achieve its goal. And these are both positive relationships where one robot can help another robot, but we also need to take into account the negative coordination relationships. So for example, a negative coordination ship might be a prevent relationship. So if this robot stays in this location here, then he prevents this robot from achieving his goal. That's a negative coordination relationship. Other types of negative coordination relationships would include, for example, hindering relationships, where one robot does something which hinders another robot from achieving their goals. So coordination requires being able to understand each other's goals and each other's actions to take those into account and predict them. And two fundamental modes of cooperation and coordination are what are called task sharing and result sharing. And task sharing is where the components of a task are broken down into smaller pieces and distributed out to other agents. So for example, these two agents can help each other by sharing tasks, right? So this agent can delegate some of its tasks to this robot while this robot delegates some of its tasks to this robot, right? And in that way, they can help each other out while they carry out each other's tasks. And the second mode of cooperative problem solving is result sharing. What that means is sharing information about what's going on. And this is the kind of thing that we saw over here. And we might see result sharing and task sharing in this disaster robotics scenario. Okay, let me talk now about a very specific technique, which is one of the fundamental protocols that's been developed within the multi-agent systems community. And this is a protocol for task sharing amongst agents. And it's called the contract net protocol. And the contract net protocol is the kind of protocol that we might find here. Imagine that this robot has discovered that this stairwell here is blocked and it needs help to clear it. And it needs help from, let's say, a bulldozer robot or a crane robot, something that's got those kinds of capabilities. And it doesn't have them itself, so how does it go about getting help with this task? So what it does is it shares that task. It gets another agent to help it with that particular task. So the contract net protocol is so cool because it's based around contracting or subcontracting in the way that that works in human society. And there are 5 basic stages in the contract net protocol. And those stages are recognition, announcement, bidding, awarding, and expediting. So let's see what that looks like. The idea of recognition is that an agent realizes that it has a problem that it wants help with. So if we go back to our disaster recovery scenario, again, we've got a blocked stairwell here, and one of the robots has encountered that blocked stairwell, and the robot realizes that it needs help to clear that stairwell. So it's got a goal that it wants help with. So why might that happen? Either it realizes that it can't get its goal achieved in isolation. You want to clear the stairwell, but you don't have the capability to do it on your own, or it can do it on its own, but it would prefer not to, typically because of solution quality, or there isn't enough time to do it on your own, and so on. In other words, you'd get a better outcome through a cooperative solution. Okay, so this is the recognition that one agent has. So what then happens is, in this stage, the agent with the task sends out an announcement of the task, which includes a specification of the task to be achieved. So it says, which is basically saying, I have a problem and I want help with that particular problem, right? So again, going back to our disaster recovery, this is where one of the robots who wants the stairwell cleared broadcasts out to all of the other robots here saying, I have this particular problem and this is the problem, this is what I want help with. So the task announcement must specify a description of the task itself to be carried out, which may be executable, right? So one way in a software environment for you to say, I want help with this task, is to send out the program that you want executed. And say, look, this is the program that you want to be executed. You would typically send out any quality constraints that you might have. So for example, the deadline by which time you want this task to be carried out, any quality constraints. So for example, one can imagine specifying if it's a scientific computation that you want to be carried out, you might specify the accuracy parameters, you might specify the accuracy of the solution that you require to be carried out. You might specify some meta task information. Look, this is how I want you to submit bids. We'll talk about bids in a moment. And finally, that announcement is then broadcast out to agents within the system. The announcement is broadcast out to agents within the system. Okay, the next stage is the agents that receive the announcement decide for themselves whether they wish to bid for the task. And there are two fundamental questions that an agent will need to answer at this stage. Needs to decide whether it's capable of carrying out the task and any quality constraints, price information if relevant. So in many applications, the transaction will be a financial transaction. So they will be bidding to carry out the task at a certain price. In our disaster recovery scenario, we don't imagine the price being a factor, but for many applications that you might think of them doing that. And if they do choose to bid, then they submit a tender for that bid. They submit a tender for that bid to be carried out. The next stage is awarding and expediting. So the manager, the agent that originated this task, receives a number of bids from different bidders, and it needs to decide who to allocate the task to, who to award the contract to. And it informs the successful bidder by awarding the contract to that bidder, who then expedites this particular task. And that may involve generating further manager-contractor relationships. So one agent which has got a task then breaks it down into smaller pieces and subcontracts those tasks to other agents and so on. If you come to implement the contract net, some questions that you need to be able to answer are, firstly, how do you specify the tasks that you carry out? How do you specify the tasks that you carry out? How do you specify the quality of service that's going to be required? What are the rules that you use to select between competing offers? If you receive multiple offers to carry out some tasks, how do you choose between those? And in particular, how do you differentiate offers based on multiple criteria? Okay. So the collection of nodes that are carried out, the collection of nodes that you've got together to carry this out is what's called the contract net. So let's see this pictorially. So this is the manager that has some, that realizes that it has a problem. I want some particular task to be carried out. That task gets broadcast out to a number of different agents within the system. So the task announcement here specifies, this is the task that I want to be carried out, any quality of service parameters, any meta task information. This is how you submit bids. Each of the potential contractors then decides whether to submit a bid. Each potential contractor decides whether to submit a bid. So here we've got two different contractors submitting bids to the original manager. The manager then decides between those competing bids. Here it's got two different bids. It has to decide which of these two potential contractors to allocate the bid to, which it does, and it allocates that bid to the potential contractor. And then the manager and the contractor have a contract established, so they are in a manager-contractor relationship, and the contractor then expedites that task. And while it does that, while it's expediting that task, this contractor may subcontract components of the task to other potential contractors. So it may generate another contract net to break that task down into smaller parts and get other agents to carry that out. Okay, I guess I've already mentioned this. This slide should have gone earlier. Apologies. This is the issue of coordination. This is where we're managing the dependencies between our actions, and those actions can be positive. So when one thing that we do enables another activity, or promotes another activity, or they can be negative dependent, where one activity prevents or impedes another activity, which requires reasoning about, modeling about other agents. Okay, let's have a look now at so that's the first. What I've talked about so far is cooperation and coordination. The contract net allows a very simple form of cooperation, through task sharing, where one agent can delegate tasks to other agents. And it's a protocol. It's a widely implemented protocol in multi-agent systems. You can, if you Google ContractNet Python, you can find examples of how the ContractNet's been implemented in Python. You can find examples of how the ContractNet's been implemented in Java and many other languages. And it's probably the most important, one of the most fundamental multi-agent protocol out there. And coordination, understanding about the relationships and solving these relationships between actions, right? The coordination problem, the problem of solving the problem of coordination of activity between agents. So this is the scenario where we saw in the robotics, these two robots need to coordinate because they can't guarantee to get their goal achieved if they don't coordinate. And that requires modeling and understanding. And understanding, for example, that my goal can prevent the goal of the other agent getting his goal achieved. And by understanding these relationships, we can allow the two agents to coordinate themselves, the two robots to coordinate themselves so that they can both get their goal achieved. The final capability that we're going to talk about, and this is the most technical example that I'm going to give. So I will give you a very specific example of how we can build agents that can negotiate. Now, to motivate this, what we're going to do is we're going to start with the following scenario, which is a scenario where we've got a bunch of agents who can benefit by reallocating tasks that have been given to them. The idea is we've got two companies, Company A and Company B. And Company A and Company B both start off at this location here, at this location 1. So in this graph, we've got each of the locations numbered 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are just locations on a graph. And the edges indicate the distance between these locations. So to go to travel on the road from location 1 to location 2, it's 5 kilometers. From location 2 to location 3, it's 4 kilometers. From 3 to 6, it's 2 kilometers, and so on. Now, these two companies both start off at location 1, and they have tasks that they want to accomplish. And the tasks are to visit different locations. So company 1 needs to visit location 5, 3, 8, and 9. That otherwise it needs to go to 5, 3, 8, and 9. Okay. While company B needs to visit 4, 5, 3, and 9. So 4, 5, 3, and 9. Okay, so the simplest way to address this problem is for company A's robot to simply find the shortest path, the shortest route, which includes visiting 5, 3, 8, and 9. Right? So visiting 5, 3, 8, and 9. And that's a well-established computational problem. It's not an easy computational problem, but we have techniques that will solve, for scenarios like this, that will solve it quite efficiently now. And then company B can just solve its optimization problem. It can find the shortest tour, which includes 4, 5, 3, and 9. And again, we can find off-the-shelf solutions which will work for examples like this, even though it's an NP-hard optimization problem. But here's the thing. They can benefit by reallocating tasks amongst themselves. So, for example, notice that both companies need to visit 5. So why doesn't company A take on the task of servicing location 5? And that means that company B then no longer needs to do that, right? But company B, as a quid pro quo, might want to take on the task of visiting number 3, right? So since company A has taken on the task of visiting 5, company 3 might take on the task of visiting 9. And then we notice that they both need to visit 9, but only one of them needs to do that. So here what we're doing is we're reallocating these tasks. Each of these locations that needs to be visited is a particular task. And by reallocating them amongst themselves, they can both benefit. So how do they do that? So here is one solution. Company A visits 5, 3, and 8, and company B visits 4 and 9, right? And you can see in doing that they both benefit. The overall cost is reduced for both of them. But there are other solutions as well. Another solution is that company A visits all of the locations, right? This is great for company B, right? So company A visits all of these. That's great for company B, but that's not very good for company A. So how do we find that reallocation of tasks amongst those two agents? And the technique that's used in multi-agent systems for doing this is called negotiation. Okay, the technique that's used for doing this is called negotiation. And what we're after is, if you imagine company A as being a software agent and company B as being a software agent, what we want is protocols and algorithms which will allow these two agents to reach an agreement on who services which locations, but we want to come out with a solution which in some sense is fair, right? We want to come out with a solution which in some sense is fair. So we don't want a solution, right? Company B is not going to be very happy with a negotiation protocol which results, sorry, company A is not going to be very happy with a negotiation protocol which comes out with this as a particular solution, right? It's not going to want such a solution. It's going to be much happier with a solution which looks like this. So negotiation then is a capability. It's a capability that we all have, and it's a capability that we want to give to software agents. And it's the process of reaching an agreement on matters of common interest. And when we think about negotiation, we will think about negotiation as being a negotiation scenario as being defined by 4 things. So the first thing is what's called the negotiation set. This is the space of possible deals that the agents can make. So the negotiation set in this sense consists of all the different ways that these tasks that the agents are given that could be reallocated amongst those two agents. So this scenario here, where agent A visits everything and agent B does nothing, we might think of that as being one possible deal that they might make. This scenario here, where A visits 5, 3, and 8, and B just visits 4 and 9, is another deal that they could possibly make. So all the space of all those possible deals defines the negotiation set. This is where agreement might be reached, right? Then we've got a protocol. The protocol defines the basic rules of negotiation, how negotiation is going to proceed. So this is the rules of encounter. This is going to govern how these two agents are going to interact with one another. Next, we've got for each agent, we've got so the protocol is literally going to govern how these two agents are. This is going to be the protocol which is going to govern how these two agents are going to negotiate with one another. The strategies that each agent has, which are private to an agent, the strategy that you use, I don't see, and the strategy that I use, you don't see. These are going to be the rules that the agents use to define how they will negotiate. And finally, we need a rule that determines when a deal has been struck and what the agreement deal is. And most negotiation protocols, not all, typically take place over a series of rounds, with every agent making a proposal at every round. So what we're going to look at is a particular negotiation protocol which has been used for scenarios like this. Scenarios where the agents will need to reallocate the tasks amongst themselves. But when we design a negotiation protocol, we typically want it to have some nice properties. So one property that we want is what's called efficiency. So a protocol is efficient in a technical sense if it's what's called Pareto optimal. So what Pareto optimality means is that there's no other solution that you could come up with which would make one agent better off without making anybody else worse off, right? Or to put it another way, that any improvement that you could make for one agent would lead to a worse scenario for another agent. An outcome, a negotiation outcome, is going to be Pareto optimal if there's no improvement that you could do which would make one agent better off without making another agent worse off. So to go back to our scenario here, if you ended up with both of the agents visiting the same location, right, then that would not be Pareto efficient. That would be inefficient because one of the robots could have visited that location and the other wouldn't have needed to, right? So that's what efficiency would mean in this kind of setting. Stability. What this means is that we don't want any incentive for a robot to cheat in the protocol. There's no incentive for a robot to do something else other than the deal which has been reached, right? We don't want an agent to have any incentive to try to cheat. Simplicity here means simplicity in a computational sense, low computational and communication cost, right? So as much as possible, we want the agents to be able to compute how to negotiate without having to solve NP-hard optimization problems or something similar to that. And similarly, we don't want a high communication cost. We don't want negotiation to go on for exponentially many rounds. We want it to terminate after a small number of negotiation rounds. As much as possible, we want it to be distributed. That is, we don't want any central decision maker. We want the decision making to be distributed across the entire system so that there is no central point of failure. And finally, we want it to be symmetric. So we want the agents to play equivalent roles, or to put it another way, we don't want negotiation to favor any individual agent, right? We want all of them to be equal players in the negotiation scenario. So what we've done in the multi-agent systems community is we've designed classes of protocols for domains that satisfy some or all of these attributes. And I'm now going to give you an example of one of these. So this is the most technical part of the talk. Okay, so here's how it goes. So what we're looking at is what's called a task-oriented domain. And a task-oriented domain is a domain exactly like the robot scenarios that we talked about here, where the scenarios where we visit a number of different tasks. So a task-oriented domain is where a robot has a number of tasks that it needs to carry out. So here, the tasks are visit location 5, visit 3, visit 8, and visit 9. So the particular characteristics of a task-oriented domain are defined by, firstly, we've got a finite set of possible tasks. So in the robots, in this scenario here, the possible tasks correspond to each of the locations that you might have to visit. So you've got 9 possible tasks that you might have to carry out. Then you've got a set of agents, the negotiators. These are the participating agents. You've got a cost function, and the cost function just says this means just for every set of tasks, what the cost of that task is. So technically, C is a function which just maps a set of tasks to the cost of that task, right? So, for example, here, the cost of this set of tasks, this is a set of tasks, visit location 5, visit 3, visit 8, and visit 9. And the cost of that task would be the length of the shortest path starting here, the shortest route starting here, that includes all of these locations and returns back to this location. That distance, which you get from these edges here, remember these edges correspond to distance, the cost of that path corresponds to the total length of that shortest path. Okay, so the cost of this set of tasks would be the total length of the shortest task, including all of those nodes. So this is a task-oriented domain, right? And an encounter in a task-oriented domain is where each of the agents, 1 through to n, has been given some particular task to carry out. So an encounter in the scenario back up here is defined by these tasks and these tasks. This is the task set for company A, and this is the task set for company B. So these are the tasks that company A needs to carry out. These are the tasks that company B needs to carry out. So this is a particular encounter. Now remember, the whole point of this is that what we're going to do is we're going to use negotiation to allow these agents to find a deal which makes things better for both of them. For example, where company A takes on the task of visiting 9, company B takes on the task of visiting 3, and so on, right? So our goal then is to find a deal which is an allocation of the tasks in T1 union T2 to the robots D1 and D2. And the cost to agent I of a deal is just the cost of carrying out its part of a particular deal, right? So if I propose a deal D1, D2, which means that, okay, so I say, well, this is where robot 1 carries out the task D1 and robot 2 now carries out the task D2, and the requirement that the deal includes all of the tasks just says that all of the original tasks have to be carried out. What a robot will do when you come up with such a deal is it will say, well, how does that compare to the tasks that I was originally allocated? So how does it compare to the cost of the tasks that I was originally allocated? And that's going to allow the robot to compute the utility of a deal. And the utility of a deal is just the difference in cost between the tasks that I was originally carried out minus the cost of the tasks that you're proposing that I now carry out. So for robot 1, he just says, well, what were the tasks that I was originally given? What are the tasks that you're proposing that I now take, and how do they compare? Now, if the task of the cost of the task that you're proposing I carry out is greater than the task that I was originally given, then my utility is going to be negative. What that means is that this deal that you're proposing will make me worse off than the deal that than the task that I was originally given. This is where an example of this would be this scenario here, right? This is not good for company B, it's not good for company A because it would make him worse off than if he'd just done the tasks that he was originally given. So this is a deal here which would make company A worse off than he was originally. Okay, so the utility of a deal is just the difference between the cost of the task that I was originally given and the cost of the task that you're suggesting that I take on in a deal. And if that utility is negative, then I'm worse off with the deal than I would be with the originally allocated task. Now, in that case, no agent will ever accept a proposal that makes him or her worse off than they would do with their originally allocated task. So if you come up with a deal delta and you say, I suggest you take this, but that deal delta makes me worse off than I would have been with my originally allocated task. In other words, the utility of that deal delta is negative. I'm going to say, no, I will carry out my originally allocated task. So for that reason, we introduce what's called the conflict deal, theta, and this is the deal which corresponds to the originally allocated tasks. So the way to think about this is if negotiation falls apart, if you come to me with a deal which would make me worse off than my originally allocated task, I'm going to say, no, I will go with my originally allocated task. So if negotiation falls apart, the worst that happens for robot 1 is that he just does the task that he was originally allocated, and robot 2 just does the task that he was originally allocated. Okay, and you'll notice that the utility of the conflict deal is going to be theta, sorry, it's going to be 0 for all of agents, right? Because the difference, it's just the difference between the task they're originally allocated and the task of the task in the conflict deal, but those are the tasks that were originally allocated. Okay, a deal delta is going to be individually rational if it weakly dominates the conflict deal. Sorry, I inadvertently became technical. Weakly dominates just means that the utility that an agent gets from a deal is at least as much as the utility it would get from the conflict deal. An individual rationality means a deal, this is a basic requirement for deals. Individual rationality is an individual requirement for deals because no agent will ever accept a deal which is not individual rationality, because by definition, it will just revert to its tasks in the conflict deal. Okay. So now a bit more terminology. So we identified the space of conceivable deals that the agents might come up with in this task allocation scenario. And that space of possible deals is just all the ways that these sets of tasks can be reallocated amongst the two agents. But now we're going to constrain that set, and we're going to say that the negotiation set is the set of deals over which agents negotiate that are both individual rational and Pareto efficient. Remember, Pareto efficient meaning that no utility is wasted. There is no way that the robots could come up with Pareto efficiency means there's no way that you can come up with a deal that makes one robot better off without making another robot worse off. So now we're going to say that the only deals that a robot is going to be allowed to propose during negotiation must be individual rational. Why? Because if they weren't individual rational, they would never be accepted by the other robot. They would just revert to their conflict deal. And B, Pareto efficient. Why Pareto efficient? Because if they weren't Pareto efficient, then another robot would simply revert to, if they weren't Pareto efficient, then we're wasting utility. And we can illustrate this graphically. So here we've got an illustration of, on the x-axis, what we're doing is we're taking the coordinates on a graph to be the utilities of two agents, agent I on the y-axis and agent J on the x-axis. And we're plotting the space of possible deals. And that space of possible deals gives us some space here, which I've conveniently drawn as a circle. So there's going to be one point where we have the conflict deal, and that's going to be the origin of this graph here. So this is where the utility of agent J is going to be 0. The utility of agent I is going to be 0. So that's the origin of this particular graph. So suppose that agent I proposed a deal which was to the left of this vertical line, right? So suppose agent I proposed a deal which was to the left of that vertical line there, right? The zero axis, the 0 y-axis. Okay. Well, agent J would immediately reject that because it would do better with the conflict deal. So it's only the deals that are to the right of this vertical line, which are individual rational for agent J. Okay, only the deals that are to the right of this line, which are individual rational for agent J. And similarly, it's only deals which are above this line, which are individual rational for agent I, right? So if agent J proposed a deal which was below that line, let's say there, agent I would never accept it because it would just prefer its conflict deal. It would prefer to do its tasks as part of the conflict deal. Okay. So what we've got then is the space of deals which are individual rational are those that are to the right of this vertical line and above this vertical line. In other words, they're in this quadrant here. Okay, so they're in that quadrant here. So now suppose that one of the agents made a proposal for a deal which was, say, here, somewhere in the middle of that particular quadrant. Well, the problem with deals that are in the space of that particular quadrant there is that they're not Pareto efficient. So what does Pareto efficiency mean? Well, it means that you can move up to this point here, and that would make agent I better off without making agent J any worse off, right? You could just move from this point here directly north to hit this this line here, and that would make agent I better off without making J any worse off. But actually, you could do better. You could move diagonally. You could move diagonally upwards. You could make both of them better off. Okay, so individual rationality requires that deals are to the right of that vertical line and above this horizontal line. That is the lie in this space here. Pareto optimality requires not only that they are on that they are in this quadrant, but that actually the deals fall on this line here. So the deals on this line here are actually going to be the ones that are in the negotiation set, right? Only those deals. Why? Because anything below that horizontal line is not going to be individual rational for agent J. Anything to the left of that vertical line is not going to be individual rational for agent J. Deals which fall below this this perimeter here will not be Pareto optimal. So individual rationality requires that they're in that segment there, and Pareto efficiency requires not just that they're in that segment, but they're actually on that perimeter line there. So the deals that our agent are going to be negotiating fall on that line from B to C. Okay, so now we know what the agents are going to negotiate over. They're only going to be allowed to make proposals which which correspond to deals on that line from B to C. We're going to, the basic rule of the protocol is that we're going to rule out any other proposals that they might wish to make. Okay. So now let's look at an actual proposal, and this is a monotonic concession protocol. And the monotonic concession protocol says that negotiation proceeds in a series of rounds, right, which is very like negotiation in the human world. So negotiation proceeds in a series of rounds. On round one, the agents simultaneously propose a deal from the negotiation set. So they simultaneously put forward a deal, one deal, which when plotted here must have to fall on that line there, that perimeter line from B to C. And now agreements of reach, if the rule for defining agreement is reached if one agent finds that the deal proposed by the other is at least as good or better than its current proposal. So in other words, if you've made a proposal which makes me at least or better off than the proposal that I currently make, then we've got agreement and we're done. And if agreement is reached, then negotiation immediately ends, and it ends with the agreement deal. If no agreement is reached, then negotiation proceeds to another round of simultaneous proposals, where we see if one of the agents has made a proposal which is at least as good or better than the proposal of the other. And the way that we do that, remember, is by looking at the utilities of the deals that are being proposed. Okay, and we've got two constraints. We've got two constraints on this protocol. The first is that no agent is allowed to backtrack. So in round U+1, no agent is allowed to make a proposal that is less preferred by the other agent than the deal that it proposed at time U. That is, if I make things more attractive to you, then I'm not allowed to backtrack and make things less attractive to you. The upshot of that is that the two agents, when they negotiate with each other, are essentially going to move monotonically closer. Every round, they must move monotonically closer. They can't move further away. And finally, if neither agent makes a concession in some round U, right, if both of them stay put, they make the same proposal, then we say negotiation is over. And negotiation ends, and the deal that's selected is the conflict deal, the deal which consists of the tasks that they were originally given. Okay, so they simultaneously make proposals, and those proposals must come from the negotiation set, the set that lies on this line here. They're not required, they must never backtrack. So intuitively, agent I that starts heading down this line, making concessions towards the other agent, is never allowed to go back up this line. Right? Similarly, agent J is making concessions to agent I by moving up this line here, is never allowed to go back down this line and make things which are less preferred for agent I. And if they both stay put, so if agent I starts by making this proposal and agent J makes this proposal, and then they make the same proposals in subsequent rounds, then we say negotiations fallen apart and we implement the conflict deal the deal consisting of the task that they were originally given, giving them both a utility of 0. And the point being that pretty much any deal on these lines here, right, will make the agents better off. And if you look at this deal here, B, is the optimal deal for agent I. This is the most preferred deal for agent I, because it's the deal which, if you go over to this line here, would give agent I with the highest utility. This deal here, C, is the one that would give agent J the highest utility, and it would give agent I a utility of 0. So the question is then, how do they, they're going to meet somewhere in the middle. Where are they going to meet? Okay, so that's the protocol. How are you going to decide how to negotiate? So what we're going to put forward is a strategy, and this is just, you can implement this strategy, you can program it. It's called the Zuthan strategy. So the Zuthan strategy works as follows. So the Zuthan strategy works as follows. First, both agents start by making their most preferred deal. That is, agent I starts by proposing B, and agent J starts by proposing C. Remember, that's the deal. C is the deal that gives agent J the highest utility. B is the deal that gives I the highest utility. So they both start by making their highest, most preferred deal. So then the next question that has to be answered by a strategy is who should concede. So remember, if neither agent makes a concession, that is, if they never move closer on the next round, right, they never move closer to each other, then they both end up with the conflict deal. And that's bad, because they could have reached an agreement somewhere in the middle here, which would have made them both better off than the conflict deal. Okay, so how do you decide whether to make a concession? So the way to think about it is as follows. Suppose B, while he's been negotiating, or she has been negotiating, has made a lot of concessions, and they're in a point now where B has got down to this point here, right? So he's conceded all the way down to here. So he's given, intuitively, he's given a lot of utility. He's given all that utility to agent J. So now agent J, looking at this scenario, has to decide whether to make a concession. Now, if he doesn't make a concession and agent I doesn't make a concession, then what's going to happen is agent J is, the conflict deal is going to be implemented, and agent J is going to lose all of that utility there. It's going to fall all the way back down to the conflict deal, right? Because neither of them made a concession, and so he's going to lose all of that utility, right? If he just made a tiny concession, he would have gained all of that utility, but he didn't make a concession, so he fell back down to the conflict deal. Now, agent I, on the other hand, has much less to risk from conflict. The amount of utility that he would lose from the conflict deal being implemented is just that much there, right? So he's already conceded a huge amount. He doesn't have much more to lose by conflict. So the agent with the most to lose from conflict, if agent B has negotiated all the way down to here, sorry, if agent B has conceded all the way down to here, the one that has the most to risk from conflict is agent J, because conflict would result in the conflict deal being implemented and agent J falling all the way back down to there. So what the Zuthan strategy says is the agent that should make a concession is the one which has the most to lose from conflict. The agent which should make a concession is the one which has the most to lose from conflict. And in this case, if agent B has conceded all the way down to here, the one that has the most to lose from conflict is agent J, right? Because it'll lose this total amount from conflict over here. So the Zuthan strategy says in this case, it should be agent J that makes a concession. And intuitively, that makes perfect sense, right? B's already made lots of concessions. Surely a fair protocol would demand that it's now, if they've reached this point here, that it's now agent J's time to make a concession. So now both, if you implement the Zuthan strategy, and if everybody's implementing the Zuthan strategy, the agents can all see whose turn it is to make a concession. Okay, So the next question is, how much should you concede? So Agent J at this point knows, okay, it's my turn to make a concession. How much should I concede? Should I, for example, concede all the way down to here? Well, that's crazy. That makes no sense whatsoever. You should concede, the Zupan strategy says, you should concede the smallest amount so that on the next round, it is the other agent's turn to make a concession. The smallest amount so that on the next round, it is the other agent's turn to make a concession. Okay, so the Zupan strategy says the agents start by making their most preferred deal. On any given round, the agent that is least willing to risk conflict, or to put it another way, the one that has the most to lose from conflict occurring should be the one that makes the concession. And if it is my turn to concede, then I should concede the least amount to change the balance of risk so that on the next turn, it is the other agent's turn to make a concession. Okay. And the way to think about the willingness to risk conflict is that if you've conceded a lot, then your proposal is now near the conflict deal. In case conflict occurs, you're not much worse off, so you are more willing to risk conflict. So an agent will be more willing to risk conflict if the difference in utility between its current proposal and the conflict deal is low, right? Which is exactly what we said here. The difference in utility for agent I between its deal here and the conflict deal, which is given by this line here, the amount of utility it would lose there is just that amount, whereas the amount of utility that agent J would lose by the conflict deal is that delta there. Now, here's a nice thing about the Zupan strategy. What we said is when we gave our list of protocols, when we gave our list of desirable properties of multi-agent protocols, we said that one of the properties that we wanted is something that we called stability. And what stability means is that no agent has any incentive. No agent has any incentive to cheat. And the way that we capture this is by using a concept called Nash equilibrium. Nash equilibrium is a concept from game theory. And what Nash equilibrium says is that neither agent has any incentive to deviate, to do anything else. Now, specifically, what that means in this context, it is that if one agent is using the Zupan strategy to negotiate, then the other agent can do no better than use the same strategy itself. So this is a quote from the developers of this protocol called Rosenstein and Zlotkin. And they said, this is what they said, this is particular interest to the designer of automated agents. It does away with the need for secrecy on the part of a programmer. An agent strategy can be publicly known, and no other agent designer can exploit that information by choosing a different strategy. In fact, it's desirable that the strategy be known to avoid inadvertent conflicts. In other words, if your agent is going to negotiate, then it's actually in its interest to publish its code. It's publish its code for the Zupan strategy and to say, look, this is the code that I'm going to use to negotiate. This is the Zupan strategy code that I'm going to use to negotiate. Why is it its interest to do that? Because it means that no other agent can benefit by doing anything else other than by using the same strategy. Now, it turns out that in the Zupan strategy, if you use the Zupan strategy, what you end up with is, firstly, you end up with an outcome which is on that line. So it's Pareto efficient, it's individual rational for both agents, but it's also what's called product maximizing, which means that roughly speaking, you're going to get outcomes that are on that diagonal there, in which the benefits of negotiation are fairly divided by the two agents. They're fairly divided by between the two agents. Right? So it's a fair protocol in the sense that it divides the benefits of negotiation reasonably between the agents. Okay, so we've covered quite a lot here in my talk. If we go back to the very beginning, what we talked about are these trends in computing and where are they taking us? Ubiquity, interconnection, delegation, human orientation, and intelligence. And my point being that these are trends that are going to be ongoing throughout the future of computing. And if you think about the different versions of the future, all these different versions of the future, cloud computing, peer-to-peer, ubiquitous computing, the semantic web, the Internet of Things, and so on, the version that's most relevant for us is called multi-agent system. And that's the idea of having agents, AI systems, which are ubiquitous, interconnected, act autonomously on our behalf, are intelligent and understood and programmed by human-like metaphors. And the idea of moving on beyond the idea of passive servants to software as proactive cooperative assistants, we've seen a part of that version be realized in the form of Alexa, Cortana, and Siri. These are all implementations of that dream of having agents that act proactively on our behalf. But the version of the future that isn't there yet is the idea of these agents interacting with one another. The idea that my Siri will interact with your Siri. And that's the dream of agent-to-agent collaboration. To date, most work on agent interaction is focused on human-agent interaction. I'm interested in agent-to-agent interaction. The idea of having software agents that work on our behalf, interacting with other software agents to achieve goals. I've talked about the kinds of skills that agents, software or hardware agents, might need to be able to have. So the ability to cooperate, for example, by task sharing or results sharing. The ability to coordinate, to understand how our goals and our interactions interact with the goals and interactions with other agents. For example, via these coordination relationships where my activity enables your activity or my activity promotes your activity. We've talked about the ability of agents to share tasks, for example, via the contract net, where a manager realizes that it has some problem that it wants help with, so it broadcasts an announcement of that task, and other agents then bid for that task and become potential contractors. The manager decides amongst those and awards the task to some particular agent, which then establishes a manager-contractor relationship between those two agents. And the kind of things that you need to think about are how to specify the tasks that you want to carry out so that other agents can understand them. You need some kind of common framework there for specifying tasks, specify quality of service. How do you choose between competing bids? How do you differentiate between bids made on the basis of multiple criteria, and so on? And then finally, what we talked about is negotiation. And the protocol that I've described for you can straightforwardly be implemented in this particular scenario here. So this is a scenario where company A needs to start at this location and carry out these tasks. That is, visit location 5 here, visit location 3, visit location 8, visit location 9, and so on. Whereas company B needs to do this. And negotiation here is required to come up with possible solutions like this, where they reallocate the tasks amongst themselves to mutual benefit. Okay, and we talked about the desirable properties of negotiation protocols: efficiency, stability, simplicity, distribution, and symmetry. Incidentally, the only one that the protocol that I've described for you doesn't satisfy is this simplicity, because finding out the cost of a tour in this particular scenario, finding out the cost of a tour involves the cost of a set of tasks involves finding the cost of the shortest tour. It's an NP-hard optimization problem. So it succeeds with all the others. It fails with respect to the simplicity. But it's efficient, Pareto efficient. It's stable because it's Nash equilibrium. It's distributed. There's no central decision maker. And it's symmetric. The agents play equivalent roles. Okay, so let me just wrap up by talking about some of the potential other application areas. And these are just a few of the areas that that people are actively working on multi-agent systems applications right now. So automated commerce, buying and selling goods automatically, trading, for example, on the smart grid, the electricity grid in the UK, and I guess I'm sure it's the same in Korea. We're increasingly seeing homes being equipped with solar panels. So they're not just consumers of electricity; they're generators of electricity, which they can buy and sell on the market. So having software agents that can doing that buying and selling on the market, potentially dealing with multiple possible bidders for the electricity that we generate. Micro commerce scenarios, you're driving in a city, there's a busy intersection. How about your car actually gets engaged in an auction to find a particular slot on that busy intersection? Connected vehicles, which are communicate with each other and cooperate with each other to share some shared space. Multi-robot warehouses in exactly the cases that I've talked about. Carpooling, you've got a bunch of people on a street, some of whom need to visit, let's say, the supermarket at a particular time. They don't all need to take their cars. So how can you negotiate to decide who should take their car on a week-by-week basis? Agent-driven business workflows. So most of us spend our lives working through workflows on where we're handling documents and processing them on through a web-based interface. Having agents that can manage that process on our behalf. Automated scheduling. Okay, this is the most trivial, but actually the most important. A huge part of my life is to do with scheduling and meetings and managing my diary, and it's very, very time consuming and tedious. So automated scheduling. If I want a meeting with you, why doesn't my Siri get in touch with your Siri? And the two agents taking into account each other's preferences, coming up with a good meeting slot. And these are just some examples. There are many, many more of those. But at this point, I think I'm done. So I will stop sharing my screen, and we've got a couple of minutes. I'm happy to answer questions if anybody has those. Oh, I have still got an audience. I was wondering if you'd all left because I wasn't seeing any faces, but yeah, I've still got an audience. That's good.
I have a question. Thank you for your every effort you made early in the morning. We are working on the AI, artificial intelligence, using the reinforcement learning, and then we are applying the reinforcement learning to a single agent, and we're going to expand to multi-agent systems. And can you give us a thought or any idea how to apply the reinforcement learning into the multi-agent systems?
Okay, so a couple of things to say. I think one of the really big challenges for agents generally, and one of the big opportunities for machine learning is in communicating to your agent what your preferences are, right? So in order for an agent to be able to do well, it has to know what your preferences are. So to use the meeting scheduling example, it needs to know, for example, that I don't like meetings before 8 o'clock in the morning and so on. It needs to know all of that if it's going to make a good decision on my behalf. So how do we communicate those preferences? And it's not feasible to just write them down and give them to the computer. So here, machine learning can play a role by looking over your shoulder and looking to see what you do, right? To learn about what your preferences are. So for example, in my case, I have 15 years of a Google Calendar. And in that Google Calendar, you can find, the days on which I like to meet with my students, the days on which I like to meet with my teachers, the weeks in the year that I like to keep clear. Machine learning can learn that information, which is all to do with my preferences, just by looking at that calendar data. And similarly, in email applications, an agent can help me understand and manage my email by looking at the way that I manage my email. So I get an email from my boss, That's always the first email that I open, right? So their machine learning has a very, very big role to play, I think, in extracting preferences from these scenarios. But I think also reinforcement learning has a big role to play in, for example, the scenarios that I gave. I mean, I gave one very specific protocol for doing negotiation. It would be really interesting to see whether we can build reinforcement learning algorithms which can learn how to negotiate in these kinds of scenarios. Rather than trying to construct the algorithm exhaustively, can we come up with through reinforcement learning, can we derive algorithms that are able to efficiently negotiate on our behalf? I know colleagues who've looked at automated trading, and they're doing this in simulation, but what they want to build is automated trading algorithms which are trained by doing reinforcement learning. So there are many applications there, I think, of where reinforcement learning can be used. But for machine learning, I think one of the most important is what's called preference elicitation, taking the preferences that are in here and giving them to the computer.
Thank you.
Hello. I'm a college student who are studying about the multi-agent systems. And I want to have a question about the future of the multi-agent systems. I studied about the PDDL, the problem domain. So I understand the algorithm, what you have talked about, and but in real world, many of the algorithms are not, many of the tasks are not so easy to explain by those ways, because the test could be so complex to explain by those ways. So solving problems with those algorithms could be very restrict. And because the more the problem get complex, the more the binary complexity increases. So I know that it is very hard to solve the problems by those algorithms ways. And other ways, such as the machine learning systems, we could handle the systems by putting what the robots test and the agents and the rewards, and we can expect. I saw an article about expecting the rewards by vector applications. But even though we could get the rewards and know how do they done, but we cannot explain those ways. Why did the agents have done that way by solving the problems with multi-agents? So I think there are two ways of solving multi-agent systems. The classical ways is by algorithms, or the ways of our machine learning. I know that both ways are very important to solve the multi-agent systems, but which way will lead the way of about the multi-agent system? How do you think about it?
Yeah, I think there's no magic answer. I think you just have to look at the scenario at hand, and that you're going to get different answers in different cases. And I think it's too early to really come to have any kind of general rules about these things. So I'm not going to be very helpful there. I think there's you just have to look at the different scenarios and see which best fits. Sorry, I realize it's not tremendously helpful.
Then do you know about other studies or?
So I think the most straightforward thing there is if you send me an email, I can give that some thought offline. And I guess the organizers can provide my email. And I'm very happy to answer some specific questions like that offline, where I can just go away and think about it for a little bit and do a Google search and see if I can find stuff that's relevant. But I'd be very happy to do that if you could take that offline.
Yeah, I'd be happy to take an email to you. Thank you.
Communicate, they use natural languages. Then how do you think about using natural languages as to communicate with agent to agent?
Sorry, I couldn't quite follow the question. Could you?
When human and agent communicate, they use a natural language. I think also agent to agent can use natural language to communicate. how do you think about that? Like,
that's good question. So there's basically three approaches that have been adopted. So agent-to-agent communication, you can either devise special languages, you can design special languages that allow the agents to communicate. And there are some examples of languages, and there are software platforms. And if you give me a second, I will put in the chat bar I will give you a link to okay, wait me a second, sorry. I'm just going to give you a link to some software for okay. Yeah. Okay, so what I've put in the chat bar is a link to a piece of software called Jade. And Jade is a platform for agent communication, which uses a particular agent communication language called FIPA. And this is a language which was specifically designed in order to enable agents to communicate. And it allows agents to request each other to do things and inform each other of things and so on. There are other examples of languages, but actually, if you start with Jade, that would be the worst one. That would be the best one. So you can either design a specific language for your problem. Another approach is allow the agents to develop a language. And so there you use machine learning for the agents to build their own language. The disadvantage, of course, is that we don't necessarily understand the language itself. I think it's not commonly used, the approach of agent-to-agent communication using natural language. I mean, it's because why would you if you could just design your own language? So that, I think, is not such a common approach. But if you're interested in agent-to-agent communication and how people have thought about it currently, then that website that I passed on to you is a good place to start.
Isn't it important to understand, make human to understand what is going on in the agent?
I would say so, yes. That's one of the big problems with AI at the moment. Yes, I think that's crucially important.
Thank you.
Thank you.
Please make your question.
So you have talked about solving the communication problem with it. If I understand it right, with the epidemic logic, you can think that the robots can communicate each other by epidemic logic, putting the epidemic logic to AI, to machine learning.
Yes. Sorry, was that a question? I didn't quite get what the question was.
Confirming what you had talked about. Adding the epidemic logic to machine learning, you think you can solve the problem with the communication?
So I think, again, going back to the point that was made earlier, I mean, I think, remember, go back to the example of the robots that are in the warehouse that can't get their goal achieved without taking into account the goals of the other agent. I think there's a huge potential there for machine learning to be able to learn these coordination regimes. How can they learn to efficiently coordinate around themselves? Because clearly at some point in the past, we did exactly that, right? We learned to coordinate in the human world, and in exactly the same way, I think there's an opportunity for us to have, to do learning which will enable agents to be able to coordinate around each other. So yes, I think that's a big potential application area for machine learning.
Yeah, thank you.
Okay, any other questions? Yeah. Is it okay to send email if we have further questions later? Okay.
Yeah, no problem. I'll happily do my best.
Okay. I also need to